Alright, so in single variable calculus, you might recall the idea of what we might like to call the chain rule. So, for example, we might have y equals f of x, right? F of x is going to be some function here. Now, x is going to be defined by another function. So we might have another function that defines x. So x is going to be equal to g of t, for example. And g is, again, that's going to be some function, right? So we have y being defined by x, and we have x being defined by t, and so the derivative of y with respect to t, well, that's going to be the derivative of y with respect to x multiplied by the derivative of x with respect to t. And so we can recall this idea from calculus, and now we might want to do something similar, but for functions of multiple variables. And so there are different cases here, and then I'm going to go over these cases, and then I'm going to try to hopefully create a more general version of what we might call the chain rule in multivariable calc. And so what that looks like in multivariable calc is that, let's say we had a function. Now this time this function is going to be defined by, and let me draw kind of like a dotted line to kind of differentiate it. And so what we might have is z equals f of xy, right? And the function f takes in both x and y, and it outputs z, and that's kind of have, it's going to be like a surface in a 3D coordinate system. And so x and y might be functions of separate, might be variables defined by separate functions, and so they might be x equals g of t, and then y is going to be equal to h of t. This is just an example. And so what might happen then is that in order to find the derivative of z with respect to t, well, what we're going to have to do is first find the partial of z with respect to x, and then multiply that by the derivative of x with respect to t. And so we remember the idea of partial derivatives, hopefully from earlier. And so we're going to use that idea of a partial derivative. We're going to find the partial with the z with respect to x, multiply that by the derivative of x with respect to t, and then we're going to be adding that with the partial of z with respect to y, multiplied by the derivative of y with respect to t. And so that's kind of one way to look at chain rule as it applies to multivariable calc. And in fact, you can kind of extend this concept even further. Let's say x and y were actually defined by two variables, s and t, for example. And so y is also defined by s and t. And these are two separate variables. Well, then in that case, then let's say we wanted to find the partial derivative of z with respect to s, or with respect to t. Then what might we do in that case? Then what we might want to do is we might say that the partial of z with respect to s is, and what that looks like is we're going to have, again, the partial of z with respect to x multiplied by the partial of x with respect to s. And so we're going to add that to the partial of z with respect to y, again multiplied by the partial of y with respect to s. And so that's specifically going to be for s. In order to do that for t, the partial of z with respect to t, that's going to look very similar. That's going to look very similar. In fact, I can actually copy this portion over here. I don't want to rewrite it again, but we can copy that portion here. And the only things we're really going to change are these variables over here. And what that's going to look like is just like this. It's going to be partial of z with respect to x multiplied by the partial of x with respect to t. That's going to be added to the partial of z with respect to y multiplied by partial of y with respect to t. And so using this idea of partial derivatives, we can essentially find deeper and deeper, using multivariable functions, we can kind of, in multivariable functions, we can actually try to find partial derivatives of functions of variables that are defined by other variables. And in fact, we can actually create a tree diagram in order to actually help us in doing this. And so what is a tree diagram? Well, let's say in this example, and in this earlier example, what we had was z was being defined by x and y, variables x and y. And those variables x and y were defined by s, and they were being defined by t. And so in order to find the partial of z with respect to s, for example, we will have to first find the partial with respect to these intermediate variables. And I'm going to write that down, intermediate. So finding the variables, finding the partial with respect to these intermediate variables helps us in finding the partial with respect to those deeper variables. And so we'd first have to pass through x. So our route is essentially going to be as such for s, and then for we'd have to go through y as well. And then for in order to find the partial with respect to y, the partial with respect to t, we'd have to go once again through x, and then we'd have to go through t. So let me draw that down. And so adding those two together would give us our respective partial derivatives. Let's look at an example of chain rule using partial derivatives. Alright, so we're asked to find, or use chain rule to find the indicated partial derivative. And so the function we have is y over 2x plus y. X is defined by p times q times the square root of r, and y is defined by p times the square root of q times r. And so we're asked to find the partial of f with respect to p, q, and r, when p is equal to 2, q is equal to 1, and r is equal to 4. Alright, this looks kind of like a monster of a problem, but it really isn't, right? Because, first of all, we know how to find our partial, we know the chain rule, right? And so that's kind of a benefit that we certainly have. Let's first try finding the partial of f with respect to x, and then f with respect to y. That's kind of going to be our small little mini goal, our goal coming into this problem. So the partial of f with respect to x. Well, we know that the function f can be rewritten as y times 2x plus y to the power of negative 1, right? And so what we're going to have is going to be del f over del x is going to be equal to, and using power rule, we bring down that negative 1. So bringing down the negative 1, we have negative y 2x plus y, 2x plus y, I wrote that incorrectly, it's the power of negative 2. And then for that inner function, or for that inner expression, we have 2x plus y, and the derivative with respect to x, treating y as a constant, is just going to be 2. And so what we're left with is going to look something like negative 2y over 2x plus y squared. Alright, so we have that partial derivative over there. Now we have to do the partial of f with respect to y. And so this is going to look a little bit different, because now we're probably going to have to use quotient rule over here, because we have kind of that y on top and we have the 2x plus y on the bottom. And so I think the best route for us here would be quotient rule. And so first we'd have to find the derivative at the top, and so that's just going to be 1. Derivative, we keep the bottom the same, so we're going to have 2x plus y on the bottom. That's going to be subtracted from y times the derivative of the bottom, and that's just going to be 1 again, over 2x plus y squared. And so I'm going to do some quick math over here. We're going to have 2x plus y minus y, that's just going to be 2x, and so what we're left with is 2x plus y. 2x over 2x plus y squared. Alright, so we have found our partial of f with respect to x and y. Now we have to find the partial of x with respect to p, q, and r, and then we have to do the same for y. And this is not going to be as complicated as you think it is, right? Because p, q, and r are just very simply written as p, q, and r, and then that r is in the square root for x. And so the partial of x with respect to p, I'm just going to remind ourselves of what that function looks like, or what that expression looks like. We have x is equal to pq times root r, And so what we're going to have is the partial of x with respect to p is going to be q root r. The partial of x with respect to q is going to be p root r. The partial of x with respect to r is going to be, now we have to bring that, the r is going to be to the power of 1 over 2. Bringing that 1 over 2 down and changing the exponent to negative 1 over 2, well, that's going to be, that's going to leave us with pr over, or sorry, pq over 2 root r. All right, so we found our partials of x with respect to p, q, and r. We can do the same for y. I'm actually going to do it to the side over here just for simplicity. So we have del y over del p. That's going to be equal to the square root of q r. Using the same principle from the previous, from x, we can say that del y del q is going to be equal to pr over 2 root q. And then finally, del y del r, that's going to be p times the square root of q. All right, so we have our partials of f with respect to x and y. We have the partials of x with respect to p, q, and r, and then y with respect to p, q, and r. And so now we just have to combine all of this, and then we have to just we have to find expressions for del f, the partials of f with respect to p, q, and r, and then actually find the partial derivatives at specific values 2, 1, and 4. Actually, we can rewrite this. We can rewrite this to the point 2, 1, 4 as such. So what's this going to look like in practice? Well, in practice, actually, here's what we can do a little bit more simply. We don't have to rewrite these expressions. Instead, we can say that at the point 2, 1, 4, at that point, the value of x, well, the value of x is going to be 2 times 1 times the square root of 4. And so that's just going to be 4. And the value of y at the point 2, 1, 4, when p is equal to 2, q is equal to 1, and r is equal to 4, well, that's just going to be 2 times the square root of 1 times 4. That's 8, right? And so del f over del x at the point 2, 1, 4, recalling our value for del f over del x, I'm just going to copy and paste that. It's much simpler. And so I'm going to copy and paste this value, and now all we have to do is substitute in our expression. So allow me a moment to substitute in the expression. Actually, let's change this value over here. Instead of 214, let's make it 48, because the value of x is 4 and the value of y is 8. So we're going to actually change that value to 48. And so changing that value, we can now sub in the values of 4 and 8, and so we'll get our evaluated value of the partial of f with respect to x. So let me do that really quickly. So we're finding the value at 4, 8, and so we're going to say that our value, actually we can remove the parentheses, we're going to say our numerator is going to be 2 times 8, our denominator is going to be 2 times 4 plus 8 squared, and so what that leaves us with is negative 16 over 16 squared. And so that's just negative 1 over 16. And so that is our partial of f with respect to x at the point 4, 8. Now we have to do that with the partial of f with respect to y. So let me write that down really quickly. So we're going to have f with respect to y at the point 4, 8. I'm going to once again recall our value, our expression rather, for del f, del y. Paste that over here. And so what is that value going to be? Well, we're going to sub in our x and our y. So what that leaves us with is 2 times 4, or sorry, yes, 2 times 4 multiplied by 2 times 4 plus 8 squared. And so that's going to be 8 over 16 squared. Now, this might look like some really complicated math, but it's really easy. We can just say that it's going to be, we're going to say that it's going to be 1 over 16 times 2, which is essentially going to be 1 over 32. All right, so we have our values for del f, del x, del f over del x, and we have our value for del f over del y. Now we have to calculate our partial of x with respect to p, q, and r, our partial with respect to, of y with respect to p, q, and r, and then we can finally get our answer. And so this might look like something very tedious, but this actually is, because realistically we have our setup, we found our setup, and now all we have to do is to do some simple algebra. Tedious, yes, but simple or hard, no. So let's do that. So first, del x over del p at the point 214. What that's going to look like is going to be, I'm going to do some quick math here. What that's going to look like is going to be 1 times the square root of 4, that's 2, del x, del q, that's going to be 2 times the square root of 4, that's 4, and del x over del r, that's going to be a little bit more complicated. That's going to be 2 times 1, which is 2, over 2 times the square root of 4, which is 2. So 2 times 2 is going to be 4. 2 over 4 is going to be 1 over 2. All right, let's do the same for y now. Let's do the same for y. And so we're calling our values for, or we're calling our expressions for y. Actually, we can realistically delete this because it's kind of redundant. So I'm going to delete this and move this up a little bit. And so I'm going to recall our expressions for y. Whoops, let me paste that in over here. And so what is going to be del y over del p at 214? Well, that's simply going to be equal to 1 times 4, which is just 4. We can do the same for del y del over del r. That's going to be a little more complicated. That's going to be 2 times 4, which is 8, over 2 times 1. So that's going to be just 2. And so we're going to have 8 over 2, which is 4. And then del y over del r is going to be p times q. And so that's simply going to be equal to 2. All right, so we have our values for del f over del x. We have del f over del y. We have del x for with respect to p, q, and r. And then we have the same thing for y. I'm going to delete this value now over here. And so now we can find del f for p, q, and r. And this is kind of the finalization of our answer for this whole problem, this whole process. So let's do it. We'll remember that del f with respect to del x, what is that going to be equal to? Again, that's going to be equal to negative 1 over 16. We also have, we have positive 32 for del f del y. Alrighty, so now to calculate del f with respect to p, so the partial of f with respect to p, what's that going to look like? Well, we are going to have negative 1 over 16 times 2, which is going to be negative 1 over 8. And then we're going to have 1 over 32 times 4. That's going to be, so that's going to be added to, that's going to be 1 over 8. That's going to be added to the negative 1 over 8. And so that's just 0. So that's our first value. Then we have del f over del q. That's going to be negative 1 over 16 times the 4. That's going to be negative 1 over 4. And then we have 1 over 32 times the 4 again. And so that's going to be 1 over 8. And so we have negative 1 over 4 plus 1 over 8. That's going to be negative 1 over 8. And then finally, we have del f over del r. That's going to be equivalent to the negative 1 over 16 times the 1 over 2. So that's negative 1 over 32 plus the 1 over 32 times 2. So that's going to, let's just keep it to 2 over 32, and so what we're left with is 1 over 32. Whew, okay, so that seemed like a very complicated problem, and in some sense it was. But realistically, we found our setup. We had our setup for what we needed to do. All we had to do was find del f over del x first. Let me bring this problem up. So all we had to do was find our expression for del f del x, del f del y, del x, the partial of x with respect to p, q, and r, and then the same for y. We evaluated it at a specific point using the fact that x and y were 4 and 8 respectively, and then using those values, we calculated our partial of f with respect to p, q, and r, and we have those values over here, 0, negative 1 over 8, and 1 over 32 respectively. Let's look at another more word problem type example. Alright, so we're being told that the radius of a right circular cone is increasing at a rate of 1.8 inches per second, while its height is decreasing at a rate of 2.5 inches per second. And at what rate is the volume of the cone changing when the radius is 120 inches and the height is 140 inches? Alright, so what does this look like, right? What is this expression going to look like? Or what is this problem going to look like for us? Well, we're being told that we have a cone as such. Whoops, let me draw that a little bit better. Okay, so we have a cone that looks something like that. Our radius is going to be over there, and our height is going to be from top to bottom. Okay, and so what are we being told? Well, we're being told that the change in r with respect to t, and we use del notation over here, or partial notation over here, that change is going to be 1.8 inches per second. That's a positive change being made over here because it's increasing. Then we have del h over del t. Well, that's just going to be negative 2.5 inches per second because it's decreasing, right? And essentially we're being asked, what is del v del t at 1.8 inches, or 1.8 inches, and 1.4 inches. All right, so with this setup, we know that we need to find our partial of v with respect to r and h. In order to do that, we need to know that the volume of a cone is going to be 1/3 pi r squared h, right? So del v over del r, that's going to be 2 pi r h over 3, and then del v over del h, that's just going to be 1/3 pi r squared. 1/3 pi r squared. All right, so now, in order to find del v over del t, what we're going to do is we're first going to set up, basically we're first going to set up our actual partial derivative. And so we're going to first do del v over del r times the 1.8. So we're going to have 2 pi rh times over 3 times the 1.8 plus the pi r squared over 3 times the negative 2.5. And now we need to find del v over del t at a specific value. And that value is going to be 120, 140. Let me delete these random lines over here. And so that value is going to be 120, 140. And so essentially, we just need to substitute in those values. So 120, the radius is going to be 120, the height is going to be 140 inches. And so what that looks like in practice is 2 pi r is 120, height is 140, over 3 times the 1.8 plus pi r squared, where r is going to be 120, squared over 3 times the negative 2.5. And so when we put this into a calculator, for example, what we're going to get is 8160 pi inches cubed per second. And so what does this mean? That means that the volume of this cone is increasing at 8,160 pi inches cubed per second at that rate. All right, let's look at one final problem which deals with the chain rule using partial derivatives. All right, so this problem is telling us that if z is defined by the function f with x and y, where x is equal to r cosine theta and y is equal to r sine theta, Well, we're asked to find the second partial of z with respect to r and theta. Now, we know this might seem like a complicated problem, and it kind of is, but I think the key here is really to break it down. And so we know what del z, del x are and del z, del y are. They're going to be cosine theta and sine theta respectively, right? And so to evaluate this second order partial, what we're going to need to do is we're going to set this equal to basically del z. We're gonna find the partial with respect to theta multiplied by del z del x times cosine theta added to del z del y sine theta. And here's where I'm kind of finding this from. Here's kind of my methodology here. We already know what del z del r is using the idea of the chain rule, that del z del r is going to be del z del x times cosine theta plus del z del y times sine theta. That's kind of that idea of the chain rule. And then we're going to find the partial of that with respect to theta. And so in order to do that, well, we first need to kind of recognize that the del z del x, and the same applies to del z del y, but del z del x is kind of defined by intermediate functions or intermediate variables as well. And those intermediate variables are x and y, which are defined by r and theta, and then y is also defined by r and theta. And so that's kind of my tree diagram for del z del x, right? And so in recognizing that, we need to also see that we kind of need to apply product rule over here. And so what do I mean by that, right? What do I mean by we need to apply product? Well, we're going to do, essentially, we're going to first kind of find the partial of cosine theta. We're first going to find the partial of cosine theta with respect to theta, and so that's going to be negative sine theta, right? And we're going to leave the del z del x the same. But now we're going to have to find the partial. We're going to add that to the cosine theta multiplied by the partial of del z del x with respect to theta. And we're going to do the same thing with the sine theta, right? We're going to say that, or we're going to do the same thing with the second term. We're going to say that the derivative with respect to theta for sine theta is going to be cosine theta. We're going to multiply that by the del z del y. That's going to be added to the original sine theta multiplied by del z del y times the partial with respect to theta. So we have that basic setup over here. And so now for these variables specifically, or for these expressions specifically, I'm going to circle them, we're going to have to evaluate the partials with respect to theta. So how are we going to do that? That's going to be kind of the complex portion of this thing, because now this is really where it gets a little bit more complicated. So we know that del z del x, for example, is defined by, and let me kind of draw some arrows over here. So del z del x is defined by x. It's also defined by r and theta. We're trying to find the derivative with respect to theta, so we have the theta over there. And then we also have the y, and that's being defined by the theta over there too. And so what we first need to do is we're going to leave these expressions the same. The negative sine theta multiplied by del z del x, that remains the same. The cosine theta is what's going to be changing over here, that expression. That's going to be del z, the second order partial derivative with respect to x squared, and then that's going to be multiplied by the partial of x x with respect to theta. And so the partial of of x with respect to theta, well, that's just going to be negative r sine theta. From here, we know that the partial of x with respect to theta is going to be negative r sine theta, because we're trying to find the partial of theta with respect to that intermediate variable over there. So once again, we're going to have negative r sine theta. Let me write that down over here. So negative r sine theta. That's going to be added to the second order partial of z with respect to y, and that's going to be multiplied by r cosine theta, because we know that r cosine theta is the partial of y with respect to theta. Alright, so having done all that, we can close these parentheses, and so now we've found that first expression. Now we can do it for the same for the second one. We're leaving that first cosine theta the same, the cosine theta del z del y the same. Now we can have the sine theta, we can change that sine theta expression. So what's that going to look like? Well, it's going to look almost the exact same as the previous second order that we did. We know that we're first going to do the partial with respect to x, and so the second order partial of z with respect to x and y, that's going to be multiplied by negative r sine theta, and then because that is kind of how that tree diagram goes, and then we're going to multiply that by the second order partial of z with respect to y squared, and that's going to be r cosine theta. Close those brackets, and then we are basically done. And so now we can actually go ahead and simplify this expression, this very complicated expression. And I can very clearly see that we're going to have to combine some terms, namely this del z, the second order del z with respect to x and y, both of these over here. And so I can definitely see that coming up in the long term. But first, let's first do this. Let's first simplify this expression, starting out with the negative sine theta. And so I'm going to write the negative sine theta del z del x plus the second order partial of z with respect to x squared multiplied by negative r sine theta cosine theta, cosine theta. Actually, we can take out this negative over here. We can take out that negative and just put it up front. So I'm going to put it up front. Okay, as such, we're going to distribute that cosine theta over here now. And so we're going to have the partial multiplied by r cosine squared theta. Okay, so that's that top portion over there. We're going to be adding that to cosine theta multiplied by the partial of z with respect to y minus the second order partial of z with respect to y squared, r sine theta cosine theta, once again, cosine theta. And in fact, I actually made a small error over here. That's going to be positive, in fact, because that sine theta multiplies by the cosine theta. That's a positive addition being made over there. And then sine theta being distributed to the first term, well, that's just going to be negative del z, the second order partial of z, with respect to y and x. I'm going to reorder that, y and x, that's subtraction happening over there, multiplied by r sine square theta. And so how can we combine these terms now? This is pure algebra now. This is pure algebra. And so in order to combine these terms, well, we can clearly combine this r cosine square theta and that r sine square theta. And so what that's going to result us in, or what that's going to get us, essentially, is and so we can definitely, and so what that's going to get us. And so we can definitely combine these two, that partial of z with respect to y and x, we can definitely combine that. And so that's going to be r cosine squared theta minus r sine squared theta being multiplied by that term. Then we're going to have that r cosine theta. That can be combined over there, and then we're going to have two remaining terms. And so what that's going to look like in the end is cosine theta del z del y minus sine theta del z del x plus, I'm going to use plus over here, plus r sine theta cosine theta multiplied by the second order partial of y squared minus the second order partial of z with respect to x squared. And that is going to be added to, the second order partial of z with respect to x and y multiplied by the r sine squared theta, r cosine squared theta minus r sine squared theta. And that is the end of that expression. And that is our final answer. Whoops, that is going to be our final answer. Let me box that correctly. All right. I'll be posting, of course, the solutions and the exact PDF of this whiteboard onto the description of this video. Thank you so much for watching. If you have any questions, please feel free to leave them in the comments. Otherwise, once again, thank you so much for watching, and yeah.